Continuing in chapter 13, equilibrium, we're going to do LeChatelier's principle. LeChatelier's principle says if a system at equilibrium is stressed, the equilibrium shifts to offset the stress, and it generates a new equilibrium. Now, a great deal of what we know about equilibrium comes from the work of Fritz Haber. Fritz Haber worked in the early 20th century, and what he was doing was trying to figure out how to, in particular, make ammonia. And in order to make ammonia, you have to take nitrogen as a gas, react it with some hydrogens to make ammonia. Now, you need ammonia if you are going to make gunpowder. And if you've got limited resources, you're going to have to figure out how to do this. So, he did a great deal of work on this reaction, trying to figure out how to make more ammonia. So, LeChatelier's principle. When you put a stress on a system at equilibrium, it adjusts to offset the stress, and it comes to a new equilibrium position. So the first thing that we can do is that we can change the amount of a reactant for a product, and we can change concentration. So if we have a nice system at equilibrium, if we take and we add something, so if we take a note that we're going to offset the stress. So if we take and we add a reactant, our equilibrium is going to shift away from the reactant. If we take and we add a product, the equilibrium is going to shift away from the product. So if we add ammonia, we now have too much ammonia, and the equilibrium shifts towards reactants, meaning that the ammonia reacts to make more hydrogen and more nitrogen. If instead I add nitrogen, if I add nitrogen, I have too much nitrogen, and its concentration is going to go up. It is a reactant, so it's going to shift away from it. I can equally decrease. So if I wanted to figure out how to change this, and I decrease the amount of ammonia. So if I take and I have my reaction of nitrogen plus 3 hydrogens, goes into equilibrium with 2 ammonias, and I decrease the amount of ammonia. If I decrease the amount of ammonia, the reaction has to shift to fill that back in again. So if I take and I decrease, it's going to fill in. The reaction will shift and make more of it, so it will fill it back in again. And if I increase in the concentration, it will make less. It will shift away. It has to shift away to offset the change. So again, the key is offsetting. Decrease makes more, increase shifts away from. And this is, for example, how you actually do this in industry. So if we start out with nitrogen and hydrogen, and we take and we put it at really, really, really high pressure, we throw in a catalyst, which is going to speed up the reaction. Now, it's not going to change the position of the equilibrium, but it will speed it up, and it's going to allow it to react. Now, when it does this, nitrogen and some of the hydrogen and nitrogen are going to go away. Now it's going to come over onto this side, and it's actually going to condense it. And it's going to condense out preferentially ammonia. Well, if ammonia is preferentially condensed out, so I take my nitrogen and my 3 hydrogens, and I'm making ammonia. And then over on this right side here, I constantly remove the ammonia. My reaction is constantly going to make more ammonia. The high temperatures are to increase the kinetics. High pressure is to take and force the reaction also towards the products. So, LeChatelier's principle. If we increase the amount of product, we have too much product and it's going to shift away. If we decrease the amount of product, we now have too little product, and it's going to shift towards. If we increase the amount of the reactant, it's going to shift to make products. If we decrease the amount of the reactant, it is going to shift to make more of it. So we could mess with the equilibrium by changing the concentrations. So let's consider LeChatelier's principle as it comes to changing volume and pressure. And so realize on the reactant side, we have 2 moles of gas. And on the product side, we have 1 mole of gas. So this is going to be affected by the volume of the container or the partial pressure. Please note if I take and I increase the volume, that is going to decrease the pressure, and it's going to give it more space. Well, if it gives it more space, it's going to shift to the side with the most moles. If I take and I compress it, if I compress it, I'm going to make this side with 2 moles of gas very uncomfortable. And by compressing it, I can increase the pressure or decrease the volume. And when we compress it, we're going to shift to the side with the fewer moles. So again, if you compress, you're going to go to the side with fewer moles. If you expand and give it more space, you're going to go to the side with the most moles. So what about temperature? So there's multiple ways of doing this, but the easiest way to look at it is to imagine if your temperature here is part of the reaction. So let's say that we have calcium carbonate is going to react and go into equilibrium with calcium oxide and carbon dioxide. This reaction is endothermic, meaning that in order for this reaction to work, you have to add heat. So endothermic reaction. If we have an endothermic reaction, we're going to have a positive delta H. We have an exothermic reaction, we are going to have a negative delta H. And if we have a positive delta H, or just imagine that we have a endothermic reaction and we add heat, if we treat heat as a reactant and we add it, we're going to shift away from it. If we decreased the heat, it would be decreasing this amount and it would shift towards this. Also, the better way to look at it is that if your reaction is endothermic, your K is physically going to get larger and it will shift towards products. But looking at it as a reactant or a product is a little bit easier. Let's say the reaction instead is exothermic. So if I take water as a gas and I go into water as a liquid and I add heat to this, if I want to take and make water as a liquid, I know I have to do this cold. If I do this hot, the reaction is going to go towards water as a gas. So here, if my reaction is exothermic and I take and I increase the heat, my reaction is going to go in this direction. If I take and I decrease the heat and I make this nice and cold, my reaction is going to shift towards product. So if my temperature goes down, I'm going to shift towards product. If my temperature goes up, I'm going to shift towards reactants. So let's put it together. So one, we can change the equilibrium constant. If we change the temperature, we are going to shift the equilibrium and change the value of the equilibrium constant. We add a catalyst. This is kinetics. This will not change the equilibrium or the equilibrium constant. It will change the rate. It will allow the reaction to go faster. Now, on the other hand, if I change concentration, pressure, and volume, it is going to shift the equilibrium. Temperature will shift the equilibrium as well, but it does it by actually changing the value of the equilibrium constant. So LeChatelier's principle in practice. For the reaction of 2 SO2s plus O2 goes into 2 SO3s, where I have a nice exothermic reaction, which means heat is produced. Heat we can consider to be a product. Note, if it is an exothermic reaction, if I take and I increase the temperature of an exothermic reaction, the K is going to get smaller. So let's play with this for a moment. If I add more oxygen, oxygen is a reactant, so if I add a reactant, it's going to shift towards products. If I remove SO3, SO3 is a product, and my SO3 contents go down, and I'm going to shift towards products. If I compress it, I'm going to go from 3 moles of a gas to 2 moles of a gas, and it's going to shift to the side of fewer moles, and it's going to shift to the product. If I decrease the temperature, if the temperature is going to go down, it's going to shift towards the products. If I double the volume, it shifts to the side with more moles, and it's going to shift towards reaction. If I warm the mixture and my temperature goes up, so if my temperature goes up, it's going to shift away and make more reactants. I can add an inert gas and you go, whoop-de-damn-do. You're right, no effect. It's not part of the reaction. If I add a catalyst, it will speed it up, but it's not part of the balanced reaction, so it's going to have no